Here are a couple of simple exponent problems, and by simple I don't mean easy, but they're pretty straightforward if you follow along. Whenever I have variables in an exponent like this first one, 2 times 2x minus 1 equals 32 times x plus 2, the first thing I'm looking to do is simplicity. If I can assign these exponents equal to each other, that'd be nice. And I notice that 32 is a perfect power of 2. In fact, it's 2 to the 5th. If you didn't notice that, then this problem hopefully is not too terribly difficult for you. But if you see that, now I can distribute these exponents, right? 2 to the 5th to the x plus 2 means I multiply these two things. So I'm going to distribute that, which would be 5x plus 10. 5x times 5 plus 2 is plus 10 there, and now 2 to the 2x minus 1. The reason I did this is because the analogy I've used in class is 3 squared equals 3 to the x. Everybody says, oh yeah, that's 2. If the base raised to an exponent equals the same base raised to an exponent, well, the exponents have to be equal. And that's why I did this. Now I have 2 raised to this power equals 2 raised to this power. These two powers, these two exponents, must be equal because the base is equal. It has to be. Okay, so now I don't need to worry about exponents or logarithms or anything. I just set these things equal, and I'm going to do the algebra from here. Okay, subtract 10, I get minus 11 from each side. Okay, subtract 2x, I get 5x minus 2x is 3x. And if I do the math, divide by 3, I'll get minus 11 thirds equals x, and that's that. Pretty straightforward, but you had to see that 32 is a perfect power of 2, and then do the math simply there. Okay, the other one, 5 equals 9 to the x plus 1. Let's do that in a different color here, if that helps at all. 5 to the, let's see, 5 equals 9 to the x plus 1. 5 equals 9 to the x plus 1. Right off the bat, there's no way I can make 5 and 9 have the same base. 5 is a prime number. 9 does not have a multiple of 5 in it, so it's not going to work. Okay, this is 3 squared, and I could try that, but that's not going to help us. Okay, what you've got to do here is you've got to do your logarithm. You've got to, whenever you see a variable or an unknown like x or a or b or n or whatever it is, whenever that unknown is up in the exponent, the only way to bring it down out of the exponent and solve it is through logarithms. So I've got to take this to a log and then use the skills I've learned this week to find x. Okay, so what this means is when I make this whole thing into a logarithm, remember it's the number that's being raised to an exponent that becomes the base. So this means log base 9 of some power, okay, equals 5. Okay, what you've learned from the log base is this to that power equals 5. Remember I said left, right, left, left, right, left. So 9 to that power equals 5. So I've taken this and done it in reverse order. If this 9 is raised to that power, then I can write the log of log base 9 of 5 equals x plus 1. 9 to this power equals 5. Now the reason I did that was because we've learned now that log base 10, which is what your calculator does, divided by log base 9, the base always goes in the bottom of the fraction. I can punch this into my calculator and get a decimal answer, and that's equal to x plus 1 now. That's why we did it. That's why we learned logs, to solve exponential problems like that. Okay, so when I do this, okay, log of 5 turns out to be, I think, 0.699, something like that. And log of 9 turns out to be 0.9542. And that equals x plus 1. So when I do the math here, 0.699 divided by 0.952, I think either way, I think I get a final answer of minus 0.2692 equals x. So I skipped a step here, but if you do the math and then subtract 1 from each side, you'll get this. Okay, so I think that's my final answer for x. There you go.